Good evening, everyone. This is Celso Batalha, Astronomy 10, Descriptive Astronomy, Summer Astronomy in Evergreen Valley College. And let me go over, first of all, sharing my screen so you see what I'm seeing. And there you go. And that's where we are today. We are July 17, still in stellar evolution. I uploaded yesterday chat where I explained Hertzsprung-Russell diagram. It's a key, one of the key aspects of our course is to know how to interpret this diagram. What are the mandatory assessments? We have a discussion going on that is based on a particular location in the HR diagram that you have stars, that when you observe the stars in their luminosity and you find independent methods to pin down their surface temperature, there is a location in the HR diagram that you find stars that are leaving the main sequence, which means they are done with their evolutionary phase we call main sequence, where they spend most of their lifetime, more than 80%, 85% of their lifetime. In the same location, you find the stars that are still in the process of being formed, that they are contracting, and they are called pre-main sequence stars. Okay, so you have these two groups of stars, so you observe them, and then you find properties of luminosity and surface temperature, and you put them in the HR diagram in the same location. So how can you distinguish and determine if they are young or old? You cannot ask the star, okay, how old are you? You can't do that. So what sort of a explanation would you come up with in order to determine if a star is young or is an old star? What would you do? So that's the discussion. I didn't get a lot of input, by the way, and those inputs I got, they need some development. So don't leave to the last moment because I will not have time to provide input and feedback. We also have a homework, and what I would like to do today is to go over some exercise in stellar evolution or HR diagram that might help to better illustrate what that is. HR diagram or Hertzsprung-Russell diagram is one that relates luminosity and surface temperature, and I like a lot to use the applet, Nebraska applet, Hertzsprung-Russell diagram, and let's bring it in. And let's bring it in. And let's bring it in. Oops. My Safari is not charging, huh? I have to use a different browser. Sorry about that. We can fix that. Go. that should bring. Oh no, don't the one. There. So the the Hertzsprung-Russell diagram is one that has in the vertical. This is the vertical axis, luminosity, and in the horizontal axis, temperature. So if you take a scoop of stars in the galactic disk, this is what you see. You see that most of the stars that happen to be in the galactic disk, they are subluminous. Sub means they have small luminosity. This is the solar luminosity is 1. So the sun is right here. This red cross, that's where the sun is. So if I move away, that's not the sun. This is the sun right there. And the sun is fixed in this part of the diagram. But if I move this cross in different locations, I can see what type of star I might be able to see. But the point is, the sun is somewhere here. There you go. I could, yeah, there you go. That's the sun right there. So if we take a scoop, take the Big Dipper, like a big scoop, and scoop stars in the galactic disk, that's what you'll find. Most of them are subliminous. As you can see by probing their temperature, they are not hot, right? These are hot stars, so most of them are cool stars. Because they are cool stars and because they are subliminous, they are not big. They are small, in fact. And in fact, oops, something happened here. In fact, their sizes, you can see their sizes by these lines indicating their sizes. 0.1 solar radius, that's the symbol of solar radius. 0.1 is 10% of solar radius. So those are the stars right here. So one solar radius are here. So the stars in those two lines here, these stars are either solar or 10% of solar radius, just to give an idea how small they are. And that is the average star in the galactic disk. Okay. Now, but 90% of the stars, or large percentage of the stars, are that type. But I could also show something interesting here. If I bring stars in the night sky to my telescope and observe them, and I derive their stellar properties, and I place them here, that's what I found, that most of the stars that are bright in the sky that I can see it, they are either giants, see, the region of giants, or some supergiants, or they are somehow bordering the main sequence, see that? Or you could say they are leaving the main sequence. They are not exactly in the main sequence. They are away from the main sequence. So what we learn is that 90% of the stars in the galactic disk, they are main sequence. So they are undergoing that slow process of producing energy by fusion reactions in their very central core. And that energy being released is the one that keeps the star stable and balancing out the gravity of, or the star mass or the star weight. So you have together a contracting force, which is gravity, that tends to bring the star to the central part. And as we probe the core, the temperature in this region is the highest in the star, and also is the region that has the highest density. And those two conditions are sufficient to favor nuclear reactions by which hydrogen atoms are converted to helium atoms, and then energy is released. So that energy is the one that keeps the star stable. The star does not expand dramatically. The star does not collapse dramatically. The star is just right, stay the same size for a long time, and that has been so good for us because life here on Earth developed because of the stability the sun provides. I mean, life doesn't like sudden changes. Like our Earth now is being challenged by climate change in response to the global warming caused by the carbon footprint we are responsible for. and then we better start reducing our carbon footprints. Charles, hey Charles, how are you doing? Good to see you. Can you hear me? Hello?
Hello?
Can you hear me? You can hear me now?
Yes, I can hear you.
Okay, very good. Yeah, because yesterday you put a message that you couldn't hear. My phone was fine.
Oh, that's weird.
Yeah. Anyways, or probably it was an old message. But anyways, I was mentioning the stability that main sequence stars provide to their planetary system, because they because of their own mass content, they have the tendency to collapse under their own weight. So the gravity force is bringing the star to the central part, but the core of the star is so dense and hot that favors conditions for thermonuclear reactions. And then when these fusion reactions occur, converting hydrogen into helium, then energy is produced, and then that energy travels through the stellar interior. Charles, you have some background noise going on. Could you please?
Oh, sorry.
Yeah.
Oh, yep.
Yeah, no problem.
Yep.
And then there is a perfect balance between these the pressure, the radiation, and the energy produced in the core exert on these interior layers of the star and the star weight itself. So we have these two conditions that are being balanced out, and they are called hydrostatic equilibrium. So 90% of the stars are main sequence, and the remaining 10% are giants, supergiants, or dead corpses like white dwarfs, neutron stars, and black holes. Another part of this NAAP module I like to explore is the interactives. So you go to interactives, and you have a range of exercises that you can use to improve your understanding about basically everything. Phases of the moon. In fact, that would be a very nice review for the final exam. In fact, I have mentioned this resource in the very few days of class. What I would like to go through is stellar evolution exercise. I recommend also to do an exercise in luminosity and apparent magnitude if you have the time. And maybe tomorrow we could go over those exercise as a way to make a review on this subject. But these exercises on stellar evolution are interesting. So the figures below show main sequence stars of various size. So the main sequence stars of various size are this, they belong to this strip called main sequence. 90% of the stars are there. And the main sequence has the characteristics that the stars are cool, they are subliminous, they are small, and they are less massive than the one that are hot on the upper left-hand side of the diagram. Let me see if I can pull the diagram here. No, I can't. Can I? I think I have to go to Google again. Just a second. Sorry about that. We don't want that. Not here. Yeah. So, in fact, I should keep this. So in the HR diagram, the stars in the main sequence down here on the lower right-hand side, they are subliminous, small, and cool. And the stars in the main sequence up here, they are hot, they are huge, right? See the size of the radius, between 1 and 10 times as big as the sun. But they are also massive. Their mass content is much larger than that of those over here. So in the main sequence, the mass grows along this line. In the main sequence, the temperature grows along this line, and the luminosity also do so. Okay, so the main sequence stars as you go from the subliminous, small, to the superluminous and huge. They span a range of masses. So if we keep that in mind, then we can go to this exercise. They are called from the interactives. And then we find the luminosity of stars, exercise 1. Okay. So imagine you're comparing. Oh no, that's not the luminosity you want to do. You want to do stellar evolution. The figures below show main sequence stars of various size. So what is being requested? Rank from least to the most the mass of the stars. So which one is the least massive and which one is the most massive? Now, to answer this question, we have to remember, as we saw here, oh, I have to take this away, right there. So the least massives are the one down here. The most massive are the one down there. So these are the least massive, and as you can see by the color here, it's kind of a reddish. And you go to the most massive, they are also the biggest and the bluest. See that? So then we can answer this question. E is the least massive. And then you go to B, D, A, and C. Okay? How about from the hottest to the coolest? Again, to answer this question, if we remember in the HR diagram, the hottest one are up here in the main sequence. So we are talking about the main sequence. Those are the hottest one. And here's the coolest one. So we go by size as well. So C is the hottest one, right? And then you go A, D, B, E. The greatest to the least, the luminosity of the stars, is the same thing. So the luminosity is the high. So the luminosity, in fact, we can see and read in this vertical scale. And up in the left-hand side are the biggest, the most luminous, the hottest. And down here are the coolest, the smallest main sequence of all. Okay, so the answer would be basically the same. So this is one of the exercises you could do, and if you don't remember, you can ask me. I can review again. So let's take another one. So in the figure below shows HR diagram with data points A to F, A, B, C, D, E, F, that represent various stages in the evolutionary path for the lives of stars. Note that only stars B, D, and E are main sequence. So B, D, and E are main sequences. So, well, that's a tough one. I have a difficulty to I can see the numbers. Somebody come in. Who is there? Oh, Charles. So I don't have the numbers here for temperature, so I don't know which temperature these represent. I don't know if D represents a star up here, right? And I'm not sure if F represents a star up here, like some star up here, or represents some star down here. So I'm not sure. So I will assume these stars represent a low mass and cool main sequence star, and then B and D are on the upper hand of main sequence star. So they are kind of a blue and hot. I don't know if my interpretation is good. I don't see the numbers, so I'm kind of a loss. I don't know where the sun is here. I know that these star F is evolved. It left the main sequence. The star A looks like a white dwarf, and C is a black dwarf. That's what it looks like. Okay. Rank from the earliest to the latest the stages in the life of a low mass star without companion. Okay, so it's a low mass star without companion. So low mass star without companion could be E, right? Certainly. That is main sequence. That's the earliest. And then evolves to become a giant, super giant. Now, if these are hot, these are super giant. Because giants, if I can show the class, there you go. So these are the giants. Super giants are up here. So a low mass start here, becomes a giant, and then start to cast the outer layers away, and then becomes a white dwarf. That's the evolution of a low mass star off main sequence. And a high mass star evolves off the main sequence as a supergiant, and then explodes like a supernova. So I would say E, maybe F becomes a giant, and then planetary nebula, and A is a white dwarf, and then C is a black dwarf when this white dwarf is no longer radiate anything. So I would say E, F, A, and C. And this B, D, I'm assuming they are high mass stars. They are not low mass stars. We need the numbers there. Okay, astronomy evolution, another one. The list below provides various stages of star formation and evolution for a low mass star and high mass star. Okay, so tomorrow we are tackling high mass stars, but we can say something about low mass stars. So rank from the earliest to the latest the stages for a low mass star without a companion. What's the difference? What happened with the evolution of a low mass star without companion? As we see in this chapter 22, the evolution of a low mass star without companion is one. The star itself starts as a pre-main sequence, becomes a main sequence, get off the main sequence as giant, becomes horizontal branch, asymptotic giant branch, and then that star becomes a planetary nebula and a white dwarf. Okay. Now, if this hypothetical star is a member of a binary system, which means has a companion, and the companion necessarily has to have less mass because the most massive stars evolve faster, then once this primary becomes a white dwarf and has completed its evolutionary phase, now is the time for the secondary to start evolve, right? Eventually, that come to us all one day. And then the secondary start expanding, becoming giant. And when that giant phase occurs, it is possible that the secondary start transferring mass to the primary, to the white dwarf. Now, white dwarf, as we learned in this chapter, has a limit to the mass it can support. It can't go more than 1.4 times the solar of our sun, solar mass. It cannot be more than that. If it is, the electronic pressure that keeps the star stable or the white dwarf stable cannot support its own weight. And if it bypasses this 1.4 solar mass threshold, it explodes like a supernova type 1. So the difference between the evolutionary path of a low mass star with or without companion is in the moment in which the secondary evolve. In case of a binary system, the secondary will initiate mass transfer that might lead to either a supernova type 1 or recurrent nova that flashes out with some periodicity, or nova that's not predictable, that's not periodical. Okay, so let's see what is being asked. Rank from the earliest to the latest the stages for a low mass star without a companion. So the earliest to the latest. So what we have here, planetary, no, nothing. Oh, you could start with nothing. Oh God. No, you have to start with something. So let's start with this. How about molecular cloud of gas and dust? That's a good beginning. And then gravity takes over. That's a good one. That's the second one. So once the gravity takes over, it forms a low mass star. And in fact, we should have a pre-main sequence, but I don't have a pre-main sequence here. But I do have O spectral type. No. G spectral type. That's a good one. That is a low mass star, G. So now I have a main sequence star G. But eventually this G star leaves the main sequence, becoming a red giant. I don't have a red giant here. Oh, I have a giant right there. Becomes a giant. So giant moves through the planetary nebula phase and the white dwarf phase. That's it. Right? Done. Now, rank from the earliest to the latest the stage for a low mass star, the part B, with a companion would be the same with the companion, except that when planetary nebula phase arrives, and then you go to the white dwarf phase, the companion will start evolving and casting gas on the white dwarf that might lead either to a nova or a supernova type 1 in case the mass of the white dwarf bypass the threshold of 1.4 solar masses. Rank from the for the least massive of the high mass stars. So the least massive is going to be the same thing, molecular cloud, and then go to gravitational collapse, and then it goes to least massive. I put O spectral type. I don't have a B here. And then it becomes a supernova type 2. Becomes a supernova type 2. And then we have a neutron star. The most mass of the high mass. So the most mass would be the same, except you go to a black hole. Okay. What is this? The figures below show HR diagram of 4 star clusters labeled A to D. What? Is this A, B, C, and D? Is that what it is? The labels are not on the figure. Okay. Rank from the youngest to the oldest, the age of the star cluster. So which one is the youngest? Which one is the oldest? So yesterday, I think we emphasized the turn-off point, which is this region here. See, this is a turn-off point, turn-off point, turn-off point, turn-off point. So this HR diagram of a group of stars formed together, they are coeval. They have the same age. So the idea here, the hypothesis is each one of these points represents stars of a star cluster, and by definition, they form together. So it's the same, it's like sibling stars. Since they form together, they will evolve differently depending on their mass. The most massive ones, they go fast through their evolutionary phases, while the low mass ends, they take their time. They are not in a hurry. Okay. So what we see here in this cluster, for instance, there are still some pre-main sequence stars coming through. See that? These are pre-main sequence still contracting towards the main sequence. Now I have a bunch of main sequence, and the turn-off point is right here. So stars at this level here, they have been completed their evolutionary phase in the main sequence, and they are living. Which means this cluster here is young and is probably not as young as this one. This is the youngest. So this has much more pre-main sequences still coming down, see that? And the turn-off point is much higher in the luminosity scale. So the stars up here are much more massive, and mass is what controls the evolutionary sequence. So when the star reach the turn-off point, they are about to die, and the most massive stars, they reach the turn-off point in a much faster than the low mass star. So this cluster would be the youngest, next to the youngest, and then this one, and then this one. So I don't know which one is A. So let's say this is, if this is A, okay, this is the youngest, next to the youngest, and then this one, and then this one. Okay. That's it. So there are several applets, other applets that helps to go and understand stellar evolution. There are good explanations out there, like Khan Academy we have in Canvas. I put a link there. It's very nice. But the main point is stars are not there forever. They come and go. And their main role in the evolutionary scheme of our universe is to provide and to form the building blocks of our cells, of our nature. The last thing I would like to show you today is astrobiological periodical table that lists, I'm pretty sure if you studied chemistry before, you've seen a periodical table. Right? The periodical table gives hydrogen, helium, and then it has lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluor. And this is not, well, I have to improve. I have to get a better one. This is not so well printed. But anyway, the main point is, and I will upload this in Canvas, it gives not only the astrophysical source of these elements here on this left upper box, but also gives the biological use of these elements in the upper right box. So for instance, the hydrogen, which is red means Big Bang. So the origins of hydrogen is Big Bang. The origins of helium, which is shown here, is Big Bang. But is also listed as low mass star. So that's what we are studying now. Helium atoms are produced as a byproduct, evolutionary byproduct of low mass stars, because carbon is converted into helium in the core, not in the star, but in the core. And some of this helium is cast off and away from the star. So astrophysical sources of hydrogen, cosmology, Big Bang. Helium, some from Big Bang and some from low mass star. But low mass star also forms carbon, and we learned that. What else? Sulfur, We haven't learned that. And pretty much that's it. So what is the astrophysical source of oxygen? See, oxygen we need, we breathe, is up here. So oxygen is bluish or purple, high mass stars. High mass stars. So high mass stars are responsible for forming nitrogen, carbon, nitrogen, oxygen, fluor, neon. So all of those comes from high mass stars: sodium, magnesium, calcium, potassium. Supernova come from rubidium, cesium, francium, and then you have all these different atoms. So the main point in this astrobiological chart is to remind us the elements we have that we depend upon so much came from stars in the past, and they completed their cycles and their history. Somehow we carry their history. We are carrying on their processes in a way, transformed in the exciting people that we basically are. Okie dokie. Any question?
No question.
Okay, very good. So, did you do the discussion? Oh, let me take the. Okay,